Hello, I'm Professor Leslie Rusch at Université Laval in Quebec City. I work within the Center for Optics, Photonics, and Laser, and within that, the Optical Communications Laboratory. I'd like to thank the organizers of this conference for giving me the opportunity to talk to you today about optical signal processing for coherent communications. Before I begin, I'd like to acknowledge my co-authors, Mingyang Liu, a PhD student with me, Joshua Lin, who was a postdoc, and Wei Shi, my colleague, professor also at Université Laval. So I'm going to start by giving you a little motivation for what I'm going to talk about optical signal processing, in particular about electronic control of the optical signal processing elements we're using. And I'm going to give you two examples, and both examples come from silicon photonics. In particular, we'll start by looking at a silicon photonic modulator, which is targeting very high bit rate and requiring both digital and optical signal processing. Then I'll move on to a second application, and in this case, I'll be looking at a silicon photonic microring resonator as a key element enabling this new application, and it's the tunability of the shape of the response of this resonator using electronic control that I'll be discussing. So for motivation, all silicon photonics is an opportunity to integrate onto one material multiple optical functions. And we can go from modulators to the manipulation of polarization to different kinds of filtering and different kinds of routing, multiplexers and demultiplexers. All of this is to manipulate the optical signals. And we can use a widely available silicon foundry in order to do this integration. And what is really remarkable about this is we're looking at CMOS compatible foundries where the digital signal processing and the drivers, all the electronics, can also be put into the same foundry. So the advantage of using a single foundry to produce both the integration for the optics and for the electronics is that we get low cost, we get low power, and we get a small footprint. So for this reason, I'm focusing on applications today that use an all-silicon solution. And the first one, as I mentioned, will be a silicon photonics modulator. This is a modulator that we designed and had fabricated, specifically targeting high-speed operation. And I refer you to this article if you'd like more details about the traveling wave push-pull silicon modulator that I'll be discussing. This particular modulator, I have a photo of it here under our experimentation, we use to push operation to 100 gigabaud. Now, what I have plotted here on the right is the frequency response of this modulator as we varied the bias voltage. And you can see that the 3 dB bandwidth varies with the bias voltage that we're choosing. And so when you take a systems point of view and we're trying to optimize the performance of this modulator, it becomes very complex because of the variability with different operating points that can be chosen for the modulator. So I'm going to discuss just a part of the approach that we use because I want to focus today on the optical signal processing. So when we look at high baud rate operation, what are the challenges? Well, basically it's bandwidth limitation, and this comes from many devices. So of course I'm talking about the silicon photonics modulator response already, but also the digital analog converter puts on severe limitations on the frequency response. So I'm looking for 100 gigabaud operation, and we can see the fall off even at 30 gigahertz of frequency coverage. Also, when we use a digital analog conversion, so a digital solution and not optical signal processing, we take a hit right away in the output voltage swing that we can achieve. Because of using digital pre-emphasis, the output of the digital to analog converter, instead of being a full, let's say 5-volt peak-to-peak going in, becomes something like maybe 3.5 or 1.5, depending on the different baud rates that we're trying to achieve. So for instance, if I take together the three components, here I have the digital to analog converter, the radio frequency amplifier or the driver, and the silicon photonics Mach-Zehnder modulator, taken together over a 40 gigahertz frequency range, we see more than 20 dB of limitation, bandwidth limitation, and therefore we have to do both digital and optical pre-compensation. So first we'll start by doing a digital pre-compensation here that basically just inverts the frequency response of the DAC. Now once we've done that digital compensation, we take an optical spectrum analyzer and we look at what is the frequency response afterwards for this entire chain. And we take that response and we invert it. And this is where we use our optical signal processing. So here, for instance, is the total response if I take into what I put in to invert the DAC and what I put in from inverting the frequency response I measured at the OZA. So this is what I would get as the total pre-compensation that I've used across both digital and optical. So now I'm going to do is start changing the split about what I did in digital and what I do in optical to not take the sort of typical approach, use all I can in electronics, then use what I can in optics, and instead look at a joint optimization. So now what I'm going to do, the first step in this joint optimization is I'm going to smooth the total frequency response. And so when I do that smoothing, I'm going to have two parts. I'm going to have something that looks like a ripple and then the smooth part. And now I know that high frequency ripples I can do more easily in electronics than I can in optics. Therefore, I'm going to start by splitting these two across the digital and the optical domain. So a completely different approach to what is done in each process. So we use the ripple in the electrical and the smooth in the optical. So now I have, again, I'm using some digital signal processing, but now it's not the inverse of the DAC. Instead, it's this ripple effect. And in the optical signal processing, instead of just observing what's on the OZA, now I use this smooth total response. Now, another optimization that I can do in how to split between the digital and the optical precompensation is to give each one of them a weight. So I assign a weight to each frequency response, and then I sweep across these weights in order to minimize the bit error rate that I achieve in my system. So here's a plot of the entirely smoothed optical response. And what I do is I take this smooth optical response and I modulate it by beta. So I don't use the entire depth. Maybe I do some other amount of weight to it. And I take the ripple, which I see in blue here, and again I use another parameter to sweep through these. So I sweep through all of these alphas and betas and I measure what is the bit error rate. For instance, here in the x-axis, I have the alpha factor, and here I'm plotting the bit error rate, and I've gotten plots for various values of beta. And you can see that when I use the 84 gigabaud operation or 60 gigabaud operation, I'll get different results on what would be the best split between the digital and the optical precompensation. So I find the sweet spot at each baud rate on what I should choose for the alpha and the beta level. And here is a summary, and you can see how these levels change quite a bit as I sweep through different baud rates. So depending on where I'm cutting off in the frequency domain is going to make a big difference on how I should do this split between digital and optical. So this approach that we used for a split of joint optimization across digital and optical precompensation allowed us to do the fastest demonstration ever for an all-silicon photonic modulator. In particular, we achieved a 1 terabits per second line rate by using 32 QAM at 100 gigabaud operation, and we used dual polarization emulation. And in fact, the post FEC overhead came out to be about 833 gigabits per second. And what's interesting is that this is the very cheap, very small footprint, all silicon solution, and we're starting to see rates which rival those of more traditional materials such as lithium niobate or indium phosphate. So this looks very good for the future with silicon photonics. Now I'd like to shift gears a little bit and go into an entirely different application. So the first application was for high speed, and now I'm going to also look at silicon photonics, but in this case we're looking at the tunability of the frequency response. So to be able to tune the shape of a filter in the optical domain. Now, of course, that would be useful also in the optical signal processing I mentioned in the first application, but now we're looking at it for an entirely different application. So this application is interested in looking at passive optical networks, or maybe fiber to the home would be a more accurate term for this. But imagine a next generation fiber to the home where we have a central office with a feeder line. It goes to what we call the remote node, and at the remote node we're going to split different wavelengths going to different neighborhoods. And when we do that split, we're also going to take advantage of this location, this remote location, in order to create what we call the smart edge of the network. And at the smart edge of the network, in this particular application I'm going to be talking about today, we're going to assume that we're putting into some 5G signals. So from the central office, we have a typical digital downlink to some customer premises, and we interrupt that in order to add in to one of the wavelength slots a new service, which is a 5G radio over fiber signal. So imagine that here at the smart edge, again, this red link here represents the downlink signal. And the downlink signal, it has a carrier for distribution of the carrier to all users, so that each user doesn't need a laser, it doesn't have any local source, it just uses the distributed source from the central office. And in addition to this typical downlink digital signal, we add in the same WDM wavelength division multiplexing band signals for radio over fiber, some 5G. And we also reserve a part of the spectrum for uplink of the signal from the customer premises back to the central office. So what I'm going to talk to you today is about applications at the customer premises. So how is it that we can use silicon photonics at the optical network unit? In particular, we'll be looking at signal processing and in silicon photonics to, first of all, detect this radio over fiber signal, which I've added to the band. We have to detect the original downlink broadband signal. And finally, we have to remodulate the radio over fiber return link, so to have an uplink. So how are we going to do this in silicon photonics? Well, let's look at the subsystem that we're going to have to design. What are our requirements? Well, here I have, again, a little drawing, the red representing the broadband, the blue representing the radio over fiber. The first thing I have to do is to strip off the radio over fiber and detect this and send the 5G signal to an antenna for wireless operation. Then the next step is now I want to drop the digital signal. And all of this, I'm taking off a little bit of the carrier because I need some carrier for detection because I'm having colorless operation locally. And of course, I have to leave quite a bit of the carrier for the uplink. So I have to suppress the downlink and have the uplink ready. So the way I'm going to do this in silicon photonics is to use ring modulators, ring resonators, micro ring resonators, and fast cascaded micro ring resonators at each point. One will be used for radio over fiber detection, one for OFDM detection, and another micro ring resonator will be used in a modulator configuration, an active configuration, so I could remodulate the carrier from the downlink and use it for the uplink. And again, if you'd like more information on these particulars of this demonstration, you can look at the publication listed here below. This is a photograph of the chip as we produced it for this demonstration. We have wire bonding for our heating of these sources in order to use our electronic control signals, in order to use thermal tuning to change the shape of the frequency response of these micro ring resonators. These are identical resonators. However, how we tune them with thermal tuning with these links will determine what the actual frequency response shape is, whether it's narrow band or wide band. And of course, here is the RF probe we used for remodulation. So this is a diagram of the functionalities that are on the chip. So we have two microring resonator cascades, one for dropping the ROF signal, one for dropping the broadband signal. We have two photodiodes on chip for that detection. And then we also have a path for the drop ports of these resonators. So after they have dropped the relevant signals, we have the carrier which remains, and the carrier comes into the microring modulator, and here we will remodulate that carrier with the 5G signal which is going into the uplink. Again, we're going to use thermal tuning to control these microring resonators and to get them the correct shape for the detection. So we use an arbitrary waveform generator to generate the signals to go onto the chip. We use a real-time oscilloscope to do reception from the photodiodes, and then of course we remodulate the signal and detect it as well. So I'm focusing on these microring resonators, which I use for dropping the different signals. And you can see here the first one in orange is for the radio over fiber detection, and I want a fairly narrow band response for that. And when I want to draw the broadband signal, of course the response has to be much wider for that. So although these are identical, by tuning thermally, I change the shape. So in particular, we start out with this nice broadband signal, and we have here the multiple radio over fiber signals, and here is we have the main carrier. Now I've shown you the shapes of the responses after tuning, and so what happens as I go through the first sort of orange frequency response here? Well, if I look at the spectrum after this resonator, we can see that the radio over fiber signal is indeed dropped, so it's greatly suppressed here. I have a zoom in on the carrier, and I can see that I took about 4 dB of the carrier to do detection. And there is some attenuation of the broadband signal because we are on the roll-off here of this filter, but we've done some pre-emphasis so that this comes out to be fairly flat after this filtering. Finally, we drop the broadband signal, and we can see that the broadband signal is greatly suppressed, and we used 2 dB of the carrier was peeled off here for detection. And so we got over 20 dB suppression of the downlink signal, and we used a very small amount of the carrier distributed carrier for our detection. So that means that we're going to have a lot of carrier power left in order to do the uplink. So this is the final stage in the link where I'm going to do remodulation. And in the remodulation, in this case, we chose to remodulate the radio over fiber signal. So if we look here on the left, we have the microring modulator design that we used for this application, and in particular this microring modulator was optimized for a narrowband operation. That is why we chose to demonstrate the radio over fiber, but of course that's a design choice that we made. It has a PIN structure with very high modulation depth and a very low swing voltage, which is important in order to achieve a low power operation. So as I was saying, here on the right we have the spectrum. So we have the original carrier and the remodulated uplink radio over fiber signal. And if you look on this drawing here, you'll see that we chose to do 2 radio over fiber signals, one on the upper band, one on the lower band. The upper band was not occupied originally, and the lower band was occupied previously by the downlink signal, and that was because we wanted to compare results for was this sufficient suppression, and do we get similar performance on the dune. Indeed, we got a very good suppression of the residual, more than 13 dB, which was sufficient for very good resolution reception. So I'd like to just make a couple concluding remarks. First of all, we looked at optical signal processing, and in particular for silicon photonics. So the question is, in silicon photonics, what can we do to exploit electronic control? And the second application, the electronic control, was in the shaping of the microring resonator frequency response. And what can we do with co-design with digital signal processing, and this was the first application, in order to get the most out of our optical signal processing and to be able to respond to the specific needs of a silicon photonic system. So in the one case of co-design, we saw that it was important to co-design the digital signal processing and the optical signal processing to get some optimization of this precompensation. And this was vital in order to achieve the 100 gigabaud. So if we had stuck to the traditional method of optimizing each one separately, we would not have been able to achieve this. Now, in the demonstration that I showed you previously, we used a wave shaper in order to do a programmable optical response. However, one of our next goals is to do this in an all-silicon solution, which is somewhat what we did in the second example I gave you. So the second example we saw was the PON architecture. This was a unique PON architecture which is meant to support heterogeneous services. So it not only supports the digital download, but it also allows us to add 5G services. And in fact, we looked at this 5G services within the idea of a future generation where we had wavelength division multiplexing. Now, in order to have this system be exploitable in a PON architecture, we needed to have flexible filtering that allowed us to look separately at the broadband digital downlink signal and the radio over fiber signals. And this need was filled by the silicon photonics solution, and we designed, we characterized, and we tested it as a system for the ONU, the optical network unit. And in particular, we demonstrated that we were able to achieve good carrier power efficiency. This is very important for colorless operation and keeps the cost down. Not only do we use a silicon photonics solution, which is low cost, but we also were able to refrain from using an optical source at the ONU. One of the downsides of silicon photonics is that there's no easy way at present to put a source onto the silicon photonic platform, and therefore having a solution which doesn't require a source is doubly interesting for this application. So why did we do our demonstration? We wanted to show that this coexistence of both the downlink and the radio over signals is practical, and that with the silicon photonics we are able to efficiently separate them. So this was a demonstration both for the idea of the architecture and also on the particular design that we looked at. And finally, the last thing we looked at was the uplink ROF modulation. So we're using an active silicon photonic component in order to do the modulation of the residual carrier. So I'd like to thank you for your attention. And in the last minute I have, I'd just like to acknowledge our partners. On the high-speed silicon photonic modulator, our partners are the Canadian NSERC Natural Science and Engineering Research Council and our industrial partner Huawei. For the passive optical network work, once again, it is NSERC and also the Quebec organization Prompt, which funded us, and we had two industrial sponsors. One was TELUS, the internet service provider in Canada, and Aoponics, developer of new integrated solutions for passive optical networks. So I thank you for your attention, and I hope you enjoy the rest of the conference.